So today I'm going to be talking about the OpenSSL PMD and DPDK and some analysis and optimizations that we performed. So my name's Jack and my co-presenter for today is Honnappa, who I'm sure you're all familiar with, who is in person today. So I guess, who am I? I'm a software engineer at Arm. I joined after graduating from University of Bristol with a bachelor's in computer science. My main interests in the field are networking, performance engineering, profiling, and security. My first major contributions to DPDK were really the changes that I'm going to go through in this presentation. Since then, I've taken maintainership of several minor DPDK components, so BitOps, Armv8 Crypto, and TicketLock. Sadly, due to travel constraints, I can't be here today, but yeah, Honnappa will be representing me. So first, we have some kind of background of where this has all come from. So what are the existing DPDK software crypto PMDs? So there's the Armv8 Crypto PMD, obviously, as the name suggests, is ARM platforms only, utilizes the AR64 crypto lib provided by ARM. And this provides performant assembly implementations of algorithms and makes use of ARM-specific instructions for acceleration. It only supports a couple of algorithms, so ASGCM and ASCBC with SHA-HMAC authentication. The library is very low level. It just has assembly implementations with a thin C API over it. But ARM does have plans to deprecate this library, and we'll talk about that more later in this presentation. There's IPsec MB, which there are kind of two versions of this. There's the original Intel's IPsec MB library, and then there's an ARM fork of this. The ARM fork has a much more minimal set of supported algorithms. It's only these two. And this also has a thinner API than OpenSSL, so a bit more similar to AR64 crypto lib. And finally, there is OpenSSL, which is what we're talking about today. This utilizes the very well-known OpenSSL library. It's widely packaged for basically all distributions. Supports an extremely large range of algorithms. Although the DPDK PMD only supports a subset of these, it's still a large subset. And it has a much heavier API. This is because they've tried to make a fairly generic API so that you can use the same API to access different algorithms. And it's maintained by the community. There's an OpenSSL Corporation and OpenSSL Foundation. So what are the problems here? Well, there's quite a high level of fragmentation. Depending on which algorithm you want to use and also which platform you're on, you may need to use different PMDs. There's the AR64 crypto lib deprecation. This is a prime candidate for deprecation, but the replacement does need to have similar performance. And there's the fact that OpenSSL PMD performance is suboptimal. Again, more on this later. So what do I think are the solutions here? Well, to reduce fragmentation, we can just try and reduce the number of PMDs. So one way to do this would be consolidate algorithm support into fewer libraries. And this is where deprecating Armv8 Crypto comes in. If we want to deprecate Armv8 Crypto, well, perhaps we can enable support for the algorithms that provides in a different PMD, for example, OpenSSL. And for the OpenSSL performance issue, well, we can optimize the way we're using OpenSSL in the DPDK PMD, and we can optimize OpenSSL itself, usually by adding a more performant assembly implementation, making use of newer CPU features, this kind of thing. So let's talk a little bit more about the performance of the OpenSSL PMD and DPDK. The OpenSSL PMD is not very often updated, which is not necessarily a bad thing, but vendors and users are more focused on other PMDs, so IPsec MB or hardware accelerated crypto PMDs. And a couple of changes and bug fixes have been made in the past with maybe not quite enough thought given to the performance implications or even introducing minor bugs. I've given some examples of these, but it's not a major issue. It's just something that, perhaps we've accumulated a little debt over time. The PMD already supports the algorithms that the Armv8 PMD provides, but the performance is much lower. The OpenSSL PMD is spending much less time in the actual crypto assembly implementation, which is where we'd expect to be spending almost all of the time. And in Armv8 Crypto, the assembly implementation interleaves crypto and authentication operations. This has some performance benefits. Instead of doing all of the ciphering and then all of the authentication, you can interleave these operations. So let's look at some of the numbers to back up this claim. Well, yeah, this doesn't look great, right? So the first bar is AH64 CryptoLib Armv8 PMD, and the second bar is the OpenSSL PMD. You can see that at any buffer size, the OpenSSL performance is much worse. And for more L cores, so the right graph is 8 L cores, this gap is even bigger. I mean, you can look, for example, at the small buffer size with 8 L cores. We're looking at, roughly 40 times slower, which is pretty horrendous. So, okay, right now, this doesn't look like a good way to replace AH64 CryptoLib if we're asking users to take such a massive performance hit. So here's a little look at the profiling of why this is happening. This is for the OpenSSL PMD. We're doing ASCBC HMAX SHA with 8 L cores. And this is on the Ampere Ultra platform, but results would be very similar on Intel we've checked. You can see that the two symbols that I've highlighted in green are where we want to be spending all the time. So this is the assembly implementation of the SHA authentication and the AES ciphering. And we're spending a very tiny amount of time in here, maybe in total less than 4%. And here is the equivalent flame graph for the AH64 CryptoLib. We're spending 82% of time in the assembly implementation. So, it's not even that this is really good. This is what we would expect. So, okay, how can we try and improve this situation? First, a little background on the OpenSSL API, for those who aren't aware. OpenSSL has a generic API, which is called the EVP API, which supposedly stands for envelope or envelope. This provides access to a wide variety of operations using the same unified API. There are cipher context structures, and these store the state for cipher operations. This can roughly be mapped onto one IPsec tunnel, and they contain things like the specific cipher implementation that you're using. So, for example, ASCBC128, the key, the IV, and some pending unciphered trailing buffer data if you're using partial updates. Context has a variety of states, and the lifecycle is a little bit complicated, but in DPDK, we're just using this, this lifecycle. So you can see we can new it, then we can initialize it by providing the data I mentioned before, so like the key and the IV. Then we can call cipher update to provide it some buffer data to cipher. And this can be called multiple times. You can provide multiple subsections of your buffer. Then once you've provided all of your buffer, you can call cipher final. And at this point, you will have some output that you expect to have. From here, you can either free it and get rid of the context, or you can reinitialize it. And when you reinitialize it, you can actually provide some slightly different information than the first time you provided. So for example, you could change the key or change the ID. DPDK stores these contexts inside the OpenSSL session structure. And this represents one flow. So it has one key, one cipher type, one direction, so encrypt, decrypt. Previously, DPDK was creating a duplicate of the context for every encryption or decryption operation. That was because these cipher contexts actually are not thread safe. So if you try and perform OpenSSL cipher operations using the same cipher context on multiple threads or L cores at the same time, you can get pretty bad results. If you're lucky, you'll get an error. If you're unlucky, you can get unexpected data, which is not really what you want for a cryptography library. So this seemed like something that was really expensive and wasteful. So we looked at, is there any way that we can stop having to clone this on every operation? We decided to go for an alternate approach. So maintaining a per queue pair cipher context clone. And this context clone has a lifetime across the whole OpenSSL session, the whole OpenSSL PMD session. Since queue pairs are only being used from one thread at a time, this prevents the thread safety issues. We're using per queue pair instead of per L core, just because per queue pair is, the number of queue pairs is generally going to be less than the number of L cores. And so, for example, if you'd only allocated 2 of your 20 L cores to OpenSSL, then we're just allocating a smaller array there. This does increase memory usage because the lifetime of these contexts increases, but it does drastically reduce the amount of context duplications that have to be performed. It also prevents a multi-threading performance issue that some of you probably will likely have noticed when we're looking at the flame graph. I can quickly go back and show it. You can see we're spending a lot of time in the AH64 LDR4 relaxed, which is an atomic operation. In fact, we're spending a crazy amount of time in this. This is 52%. I should note that this is on 8 L cores, so it's highly parallel. But the reason for this we found actually is that there's a globally maintained EVP cipher instance, and this lives inside, or there's a pointer to this inside the cipher context structure. Because it's a globally maintained instance, it uses ref counting to handle its lifecycle. And that means that every time we clone the cipher context or free them, we're thrashing the ref count. So especially for small buffer sizes with a lot of L cores, we're really thrashing this ref count, and it performs pretty horribly because these atomic operations are just wasting a lot of time. So our approach of not cloning this per buffer obviously negates this issue. So we implemented this as a patch set against DPDK. The performance increases for the algorithms are pretty large, especially for smaller buffer sizes, which obviously is because the overhead of this cipher context cloning is a much larger percentage of runtime when the cipher operations are over smaller buffers. The throughput uplift ranges from even up to 1,000% increase on really small buffers with a lot of L cores to a more modest 5% or so with 1 L core and very large buffers. The patch set was accepted and it's shipping as part of DPDK 2407. I would really like to thank everybody for their feedback and reviews, especially Nick Connolly and Watsala and Honnappa from Arm, and Kaiji and Akogoyle from the community for upstream reviews. And users of this PMD across all platforms should now be able to see crypto speedups without making any code changes. So here's a little comparison of the results that we got from making these changes. You can see that the performance gains are pretty reasonable, especially on the 8 L core graph because of the atomic operation issue that we discussed. And you can also see there's never any downside to it throughput-wise, so that's a good thing. But obviously, I would be remiss not to mention that, okay, we're still not matching the AR64 crypto-lib performance here. So we're still missing something really. So the next thing we looked at was, can we optimize the AES CVC HMAX SHA implementation in OpenSSL itself? So AR64 crypto-lib already has a well-optimized implementation of this algorithm. The algorithm combines the encryption and the authentication and uses interleaving, which means they're performed together instead of fully doing one operation over the buffer and then fully doing the other. Took this assembly implementation from AR64 cryptolib and created a PR against OpenSSL. The assembly implementation is essentially ported to OpenSSL, but there's a few small changes which had to do with rearranging some of the instructions to take advantage of some instruction fusing on ARM CPUs. So it should perform a little bit better actually than the previous one. But a patch to DPDK's OpenSSL PMD is needed to actually integrate this new algorithm support. There are some difficulties here. We have to think, should this be provided to the user as a separate algorithm? Like, for example, the user has to request interleaved AES CVC HMAX SHA, or should we just transparently switch to using it when the user is selecting AES CVC encryption and HMAX SHA authentication, which is what they would have been doing previously when using the OpenSSL PMD with this combination. So we had a couple problems when we came to integrating this with DPDK's PMD. The initial implementation doesn't support partial updates. So if you remember back to the lifecycle graph, this is when we call cipher update multiple times and we provide the cipher the buffer data to OpenSSL, not in one go, but in multiple goes. This wasn't supported for the initial port, and that's because AR64 cryptolib never supported this. It always required the whole buffer to be provided in one go. There's no way for the PMD to really inform the user that this isn't supported for a specific algorithm. There's no existing mechanism for that. So the only option would be to error out on segmented buffers when using this particular algorithm, and then document that it isn't supported somewhere. But this rules out the previous suggestion of perhaps transparently switching to interleaving, because now we'd be introducing a feature regression, right? Previously, you could do this with those two algorithms. Now you wouldn't be able to. So actually, the solution that I decided to go with here is, okay, we'll just add support for the partial updates to OpenSSL's implementation. Here's a little background on AES-CBC for those who aren't familiar. So AES is a very popular cipher algorithm, and CBC is a mode of operation. It stands for chained block cipher. So data is processed block by block, and the output of one block forms part of the input to the next block. The first block takes an IV, which is the initialization vector, and that's because, you know, if each block takes part of the output of the previous block, well, what does the first block take? That's the IV. And there's some constraints on how you have to generate this, but it's not particularly relevant. But because of this dependency, chain block ciphers are very poorly parallelizable, right? Because there is a dependency from block to block. So knowing this, how did we go about implementing partial updates? Well, we had a bit of an issue that AES-CBC and HMAC SHA, or SHA itself, process data in set block sizes, but they process data in different block sizes. So for AES-CBC, it's 16 byte blocks, but for SHA, it's either 64 or 128, depending on which SHA size you're using. The solution here is actually pretty simple. We can just increase the block size for the interleaved cipher to the block size of the SHA algorithm, because thankfully, you know, 16 goes evenly into 64 or 128. We also need to store some intermediate state, because now the buffer data is not being provided all in one go. There has to be some intermediate state being passed from one block to the next. So for AES-CBC, that's the output of each chunk to be passed into the next block. And for SHA-HMAC, that's the internal SHA state at the end of the block, which then has to be used as the initial state for the next block. The solution here is to store this inside an algorithm-specific struct, and this lives kind of a few layers nested deep inside the cipher context inside OpenSSL. So we did all this, but there is one problem still remaining, which is that DPDK crypto PMDs allow you to set an offset to at which you want to start the authentication and you want to start the ciphering. But these could be different. So you could have, you know, no offset for authentication and an offset for cipher, or you could have two different offsets for both. Previously, this was fine because we were asking OpenSSL to do the cipher and auth operations individually. So it was very trivial to use a different offset for each. It was literally just adding the offset to the pointer of the buffer that we provide to OpenSSL. But this is very hard to implement with interleaving operations, as you can imagine, because we're trying to do both at the same time. And OpenSSL doesn't really have the API features to allow this anyway. OpenSSL doesn't allow you to give an offset. We were just giving it a later start of the buffer. So this does mean we probably still need to make the user request the interleaving version of the algorithm specifically, and then document somewhere that you can't have mismatched offsets for this. Alternatively, we could fall back to a couple of other ways of doing this. One would be do the interleaved operation and then recalculate the authentication afterwards with the correct offset. Or the other one would be to use the non-interleaved operation for the start of the buffer until you reach some common starting point and then switch to the interleaved one. But again, this would also have performance implications. We would have to instantiate some new contexts for the first non-common chunks and then get rid of those. So this would only really be worth it for very large buffers. And this is why I think it would be good to understand the typical use case for these mismatched offsets. You know, if anyone in the community is using these, what is the kind of use case that you're using these? And, you know, do you have any potential solutions or opinions on how we could deal with this? Obviously, anyone who was previously using AR64 CryptoLib wasn't using this because it didn't support it. But, you know, we also want to improve the experience for people who were previously using OpenSSL PMD. So the status of this is that ARMS patches are upstreamed on GitHub as an OpenSSL PR. They haven't been merged, but we're hopefully targeting the October release of OpenSSL. This doesn't include the partial update support. That will come later. It still needs some more work internally, which the team is working on at ARM. And then once these changes are eventually merged, we can upstream the PMD changes to add support to DPDK. We have a work in progress patch for this, but it doesn't make sense to upstream it until the OpenSSL changes are finalized. So what kind of results do we get from doing this? Well, it actually starts looking a bit better here. You can see that this is comparing our previous OpenSSL optimizations to this, I suppose you could say, doubly optimized OpenSSL PMD. So you can see that we're getting much higher performance. again, there's not really any downside, and the difference is much bigger at larger sizes. And this kind of makes sense because we've optimized the assembly implementation itself. So the more buffer data we're giving it, then the more of the runtime that's going to take up compared to all the other API abstractions and stuff. So what future work is there? What considerations do we potentially have to make here? Well, one example of future work is that more algorithms can be supported pretty easily by the DPDK OpenSSL PMD, where the support already exists for these algorithms in OpenSSL, which likely it does. It's just a case of plumbing through the various DPDK Crypto PMD API aspects and utilizing the OpenSSL API correctly. In fact, there's already on the mailing list some additions to the OpenSSL PMD and other crypto PMDs. There may also be room to improve OpenSSL's performance more. One major area that we saw is EVP parameter handling. So OpenSSL uses a very generic way of providing parameters to Cypher implementations. They can all define their own parameters that they take, but these functions to provide parameters and check parameters are all string-based. So every parameter is represented by a string. And the way that's implemented in OpenSSL itself is actually just, if parameter equals this string, do this, it's just a bunch of fall through if statements. So it's very wasteful. There's a lot of string compares in there. There are some plans already for how to address this a bit in the OpenSSL project, because a lot of other users have also been complaining about this. It's a bit of a regression from OpenSSL 1.0. They have some ideas for automatic code generation for kind of tree structures based on the parameters. But there's a plan, but there's not really much concrete work being done yet. But hopefully if this does get finished in the future, then we'll get basically a free performance boost by upgrading OpenSSL. There won't be any changes necessary to DPDK, for example. And we also have some investigations ongoing within Arm itself as to whether the performance of the OpenSSL API can be improved in any other ways as well. So, okay, here's the graph that I've been waiting to show you, which is the comparison of AR64 CryptoLib versus the OpenSSL PMD with all the optimizations that we discussed before. So the interleaving optimization and the PMD cipher context lifetime optimizations. And you can see, okay, maybe this isn't the result we were dreaming of. We are getting better throughput, but only at buffer sizes larger than, let's say, 750. Below that, we're still getting a lot of our runtime eaten up by the EVP API. So for example, the parameter handling actually takes up quite a lot of this time. And then just there's a bunch of other code inside the EVP API. It's also doing some OpenSSL cleanse calls, which writes a bunch of zeros to memory after it's used it, which is a cryptographically sensible thing to do. But I believe AR64 CryptoLib didn't do this. So yeah, this is kind of where I wanted to open up to discussion from anyone, if anyone has any thoughts on, potentially deprecating AR64 CryptoLib in the future, given this context. Obviously, I can't see you. I'll rely on Honnappa letting me know if anyone. But obviously, if people don't want to bring up anything now, please feel free to either start a thread about it on the mailing list or email me directly or email Honnappa directly or anything like that. We're really keen to hear opinions on anything that we've gone through today, really. Yeah, that's it really. I'll leave you with the overall graph, which is kind of the combination of all the different iterations that we've talked through today. So.